So hello everyone. Today I'll discuss one of the simplest topic in physical chemistry, and all the physical chemistry topics start, or any physical chemistry textbook you choose. For example, Atkins physical chemistry or Levine's physical chemistry, they will start with the chapter of gas. Okay, why it is so important? Why you have to study gas? So you need to understand those things before going into the complicated stuffs. Okay. So in this video, I'll talk about the starting, or I will give an introduction to the gas chapter, and in the subsequent videos, I'll go into the details and complicated things related to the gas itself, which is itself maybe a complicated thing. Okay. First, but in this video, I'll talk about the simplest things, and I'll talk about the simple relationships, how to derive them. Okay. Now, this is the outline of the things which I will discuss in this video. So there are only three things I'll discuss in this video: state of the system, then equation of state, and another one is your ideal gas law. So these are the three things which I wanted to discuss in this video, and in the subsequent video, I'll talk about the van der Waals gas law. Okay, let us move. So before moving into, anything about the gas, I just want to discuss briefly about the classification of matter. And I believe that everyone is aware of that, but still, for the continuity, I just want to explain this. So if you look around your surrounding, if you look around, you will see that we are surrounded by few things. And for example, we have solid, we have a liquid, and have a gas. Okay, so all three things are important. Although there are many other states, of matter is available nowadays. I will not go into the detail because those are a little bit advanced topics. And if somebody asks you define solid, how you are going to define it? Very simple. Solid will have a shape, size, and volume. And liquid also have a volume, but they do not have any particular shape. Okay, but the gas, in case of gas, things are much more complicated because they do not have actually any shape. Wherever you keep them, they will take the shape. And if you take a gas and put into the container, it will fill the entire space. So this is about your, in terms of physical appearance. Now, why these things are happening? In the molecular level, you can say that intermolecular interaction is strongest in case of solid. Why in case of gas, it is the weakest. And it is the intermediate between solid and liquid, solid and gas in case of your liquid. So these are the, in terms of the molecular level. So this is the classification which I have done. And you guys must know these preliminary things. Fine. Now what I wanted to discuss one important thing. Okay, now the thing is that in any topic you study in physical chemistry, you need to deal with some of the terms. Okay, you must remember those things. Without that, it's very difficult. You will be in trouble. I'm telling. So many times things will come, so many repetition will come. If you do not understand properly, there will be confusion, and everything will be in a confusion. You will not understand anything. You may feel you have understood, but you will not understand. So one of the important thing is your system and surrounding. Now, what is system? Anything which you have chosen for our study or investigation is known as system. Okay, it can be anything. You cannot define that I will not study this, I cannot study this. So anything you study, you choose for your study is your system, and the rest. So you have a universe, and you minus system, you will get the universe. Surrounding. Okay. So surrounding plus system will give you the universe. Now systems are also classified in three different categories. You have an open system, and you have a closed system, you have an isolated system. Very simply, open system is a kind of system where both matter and energy can be transferred. For example, if you take a hot cup of tea, after some time it will get cooled down. So the energy, the thermal energy is transferred to the surrounding. Okay, that means there is an exchange is possible. And you can add more uh, tea into this cup, or you can drink from the cup. So the matter can also be transferred. Okay, so this is an example of open system. Now let us look at the closed system. Now we have 1 degree of freedom is lost. You cannot transfer matter. You can only transfer energy. You can think of a glass of water, a bottle of water. Okay, and this cap is tight, so that there is no way that you can lose any water. But uh, if the bottle contain a hot water, at some point of time, it will get cooled down. That means what? You can transfer energy. Okay, heat energy is transferring. At the same time, you are not allowing any water molecule to escape from the bottle, or you're allowed to transfer into the bottle. Okay, so this is the closed system. Isolated system, there is no degree of freedom. You are not allowed to exchange matter. You are not allowed to exchange energy. This is impossible in physical world. But one example which is very close to the isolated system is your thermos flask. So what is a thermos flask? If you take hot water, it will be hot for longer time, like 5 hours, 6 hours. Now, if you go into the deep into the thermos flask, what you will find, it consists of two chambers. So one chamber you will have your contain the things, tea or any other thing, and another chamber will be there, but these two chambers are separated. Okay, there is a vacuum is created in this two between these two chambers, so there is no water molecule is there. That means what? Uh, this how this heat is transferred. So heat is transferred, basically this water molecules will take the jiggling and transfer the heat. But since there is a vacuum, there is no water molecule, so you cannot heat transfer is extremely slow. Although 100% vacuum is impossible. Okay, so some molecule will be there, and that molecule is transferring the heat. Okay, that's why it is slow, because the number of molecules are less. So this is about the system and the surrounding, and three type of system I said: open system, closed system, isolated system. We are ready to move to our main topic. Now, what is a state of a system? Somebody may ask you, what you mean by state of a system? So, state of a system means we are asking what are the values of certain properties the system has at some instant. So, I'm repeating again. State of a system means the values of the properties of the system at certain instant. Okay, that means what? We are asking what is the value of the temperature of the system, what is the value of the pressure, what is the amount of the substance, what is the volume, what is the viscosity, and the list will go on. So you can have 100 different properties, and you may ask what are the values of these properties. If you know these values, you can define the state. The system is in this state. Okay. So state is nothing but it's a definition of the system in terms of the properties. Okay, the values of the properties. Now, fortunately, we don't have to determine all those properties. Okay, because there are certain relationship exist between these properties, and if you know some of them, you can determine the rest. Okay, so this is a wonderful thing, and this relationship or this kind of dependency is known as equation of state. Okay, so equation of state is nothing but it's an equation where many variables are connected in the help of some equation. Okay, I can the help of some relationship, so that if I know some of the properties, I can determine the values of the other properties. And the problem with this is that there are many equation of states exist. Okay, so you can have ideal gas equation, van der Waals gas equation, Bartlett equation, Dieterich equation, Clausius equation, and Kamerlingh-Onnes equation. And we'll not discuss all of them. So because every system has a different equation of state, I cannot use a single equation of state for all the things, all the systems in this universe. Okay, we'll discuss the simplest one, ideal gas equation. Once we know this, the rest is easy to derive actually. So this is the starting point, and then you can derive the rest. So what I will discuss ideal gas equation. Van der Waals I will discuss in the second lecture, and I will also discuss this Kamerlingh-Onnes equation. Okay, now we came to the derivation part, and let me just move this one so that this scientist picture is clear. So this his name is Boyle, and this is Robert Boyle, and Robert Boyle in 1600. So you can think of like how much 400 years, near about 400 years. He given this law. So what he is doing basically, he is doing some experiments. What kind of experiment he is doing? He has taken some air from the atmosphere. Think of this time, that time they had no idea of the gas and those things. Okay, so I mean the molecule concepts are very, that time you can think of. Now it may be very easy, but that time it was very complicated. Still, he has the courage to derive this equation. And what he has done basically, so I have given two plots here, black and red. So let us consider the black one. This side is a volume and this side is your pressure. Now he increases the pressure, and what he found, he increases the volume and the pressure decreases. Let us see, that's a V1, the pressure is P1, the higher pressure. Now when he moved to V2, the pressure becomes P2. Okay, what is happening? There exists a relationship between your volume and your pressure, and the relationship is inversely related. Basically, you increase the pressure, the volume will decrease. Okay, so decrease the pressure, volume will increase. Here you can see in the graph. Okay, so this is exactly the definition of Boyle's law. At constant temperature, the volume of a definite mass of a gas is inversely proportional to its pressure. Okay, that means what? You have a fixed amount of gas, fixed amount of the temperature should not change, and we just measure the volume and pressure, the relationship between the volume and pressure. Okay, I think all of you know this is a class 8 mathematics. You just remove the proportionality sign with equality, so you have to put a constant and pressure, and you can just rearrange PV equal to constant. Now let us see one more important. This is useful for many numerical applications. If you know the initial pressure, suppose initially the pressure was P1, volume is V1. Now you have changed the pressure to P2 and the volume changes to V2. But the product will be same. The product of P1, V1 should be equal to P2, V2. So this is the definition. This comes from the Boyle's law. Okay, so this is about the volume and pressure relationship. So let us look at another scientist. His name is your, I think I need to go back. His name is your Charles. And let me stop here. Yeah. So what Charles said, this is a picture of Charles. At constant pressure, the volume of a definite mass of a gas is directly proportional to its temperature. Now this time he did something different. This guy. So this is the x-axis is the temperature axis. This is your volume axis. Okay. Now he increases the temperature, and he found that the volume also increases. T1, the volume is V1. And when we move to T2, higher temperature, volume is V2. The volume also increases. So this is mathematically exactly his law. The volume directly proportional to your temperature. And you can again change it. Another constant, you put K dash, and you have T. Okay. This is another form of Charles' law, where in this form the pressure was constant. Here the volume is constant. So if volume is constant, you can have a relationship between the pressure and temperature. So at constant volume, pressure directly related to temperature. Okay, so this is the two forms of Charles law. Now let us look at another law, is your van der Waals equation. This is your Avogadro law. This is another important law. This looks pretty simple, but you can think of that that time it is very difficult. They have no idea, they have no instrument, nothing, no laptop, no mobile, no internet. So they were doing all these things. What is said, equal volume of gases at the same temperature and pressure contain equal amount of substance. Okay, let me explain this. Suppose you have two boxes, okay, some gases, and the volume of this box is 1 liter. This box is also 1 liter. The pressure of the gas is in the system is 1 bar. This is also 1 bar, and the temperature is also same. So under this condition, they contain same amount of this substance. Okay, so if this condition is satisfied, okay, then amount of the substance in them will be exactly same. So this is the statement. So mathematically, you can also write B directly proportional to N. Now, if you fix the temperature and pressure constant, the volume will depend on how much amount you take. More amount, more volume. Less amount, less volume. So this is pretty simple. But we're talking about this 1600, 1700. So that time, no concept, no instrument, doing anything is very difficult. So this is a picture of the scientist Avogadro, and so you can see his full name. This is quite long: Lorenzo Romano Amido Carlo Avogadro. Everything ends with O. Okay, so these are the three important laws which I have discussed. Now, what to do with these laws? So, what to do with these laws? Because we have a property of volume is related to your three different equations. The volume inversely proportional to temperature, which is the Boyle's law. Volume directly proportional to temperature, Charles law, and the volume also directly proportional to the amount of the substance. This is Avogadro law. The best thing to do, combine them. So once you combine it, you'll get a volume is equal to some constant Nt by P. Okay, so this N came from here, T comes from here, and P comes from there. Now, what is the meaning of this constant? So the constant is known as universal gas constant, and it has a value of 8.314. So this constant is replaced with this R, this widely used. So final equation is your V equal to nRT by P, or quite famously known as PV equal to nRT. Okay, so this is the equation which we have to use in many numerical equations, and not only this, in thermodynamics and your whole of your thermodynamics, and in biology also you have to use, physics also you have to use. So this equation you must remember, all of you must remember, PV equal to nRT. So one thing important is that everything we have talked about of system. Okay, the pressure is of the system. Okay, volume is of the system, amount is of the system. So we are not talking about the surround. So this is about the system. So I'll stop here. I'll not discuss the I'll not discuss the van der Waals and other things. I'll discuss in the next slide. So in the next video, I'll talk about some numerical applications, and then I'll talk about the other complicated stuff. So till then, bye bye. Stay tuned for my next video, and I'll stop here. So please, I'd like to know about your what do you call, your ideas about my this lecture. So please share your thoughts. Thank you.